So we're going to have to end on time. So I'll still count you into 1 minute before the end of the slot. Okay. 203, Roger, starting now. Hello, everybody, and good afternoon, and welcome to our next session for PyCon 2017. Our next speaker is Michelle Fullwood, who will be giving us a gentle introduction to deep learning with TensorFlow. Please make her feel welcome.
Okay, hi everybody. Thanks for coming. So welcome to a gentle introduction to deep learning. And this is going to be an intermediate level talk. So I'm going to assume that you know the concepts of supervised machine learning and are familiar with linear and logistic regression. So those are going to be our starting point. And our target endpoint today is going to be an in-depth understanding of the most fundamental class of neural networks, feed-forward neural networks, which look something like this. And we're going to talk about how they're constructed, why they work, and how to train and optimize them. So along this completely made-up deep learning curve, I'm going to put our target here. And the way in which I hope to make this talk gentle is by convincing you that if you meet the prerequisites for this talk, then you're not here or here, but you're actually here. In other words, if you know logistic regression, you are about 2 tiny steps away from understanding deep learning. To put things another way, if traditional machine learning is a hammer, then deep learning is just another fancier hammer. It might not look like a hammer at first, but you look at that thing, you can pick the thing up, you can start bashing things with it. It uses the same technologies that obeys the same laws of physics. But at the same time, it is a pretty weird hammer. It has all these extra knobs and whistles. And we're going to talk about what those extra knobs and whistles buy us in terms of power and performance. And we're going to learn how to do all this in TensorFlow, which is an open source deep learning toolkit out of Google. So let's talk about linear regression. And in this section, we're going to code up a linear regressor from scratch using NumPy. And as we go through this section, I want you to focus not so much on the code, but on the pieces, the ingredients, what they are and how they go together. So here's a typical linear regression problem. We're trying to predict the prices of individual houses. And we're given 3 pieces of information about each house. In other words, 3 features: floor area, distance from public transport, and number of rooms. And we're going to represent these features in a matrix with as many rows as we have houses and 3 columns, 1 for each of our input features. And we'll call that matrix X. And what we're trying to predict is this vector Y, which represents the housing prices. And here's what that looks like in NumPy. We're just going to use NumPy arrays to represent those. Next, we have to consider our model. The model is the family of functions that we're going to consider in mapping X to Y. And since this is linear regression, what we're going to do is multiply each feature by a weight and add them up. And then we're going to add an additional intercept to get our final estimate. And what that corresponds to geometrically is simply drawing a line of best fit through the data. So the parameters of this model will be the 3 weights, 1 for each feature, and the intercept. And the key operation of this model will be matrix multiplication of X by the weights, followed by addition of the intercept element-wise to get our final prediction. So that's what that looks like in NumPy. Now, the next ingredient we'll need is a cost function, also called a loss function. And we need this to measure how good or bad a set of parameters is, how close our predictions are getting to the actual values. For example, this is a really badly fit line. We can see that, but how do we measure it? What we're going to do is to take the difference between the prediction and the actual value and squaring that. Okay. So this looks a lot better because the length of those lines is a lot shorter. And that's what it looks like in NumPy. Now, we need to actually find the parameters that give us the best fit. In other words, we want to hold X and Y constant and adjust our parameters to minimize the cost. each set of parameters will yield a cost. So we can plot cost against parameter values. So the x-axis here is parameter values, y-axis is the cost. Our goal in optimization is to find the parameters that correspond to that lowest point. And we're going to do that by trial and error. And by this, I don't mean just trying random sets of parameters and seeing what works best, but the kind of trial and error you do when you're, say, practicing how to shoot hoops. And you're trying to adjust your angle, and you're shooting, you're missing by a couple of inches, you're too far to the right, so you adjust your angle to the left, and you try again. And that's what we're going to do also. So what we'll do is try a set of parameters, we'll calculate our cost, and then we'll follow the gradient of the cost curve at that point down towards the minimum. This process is called gradient descent. And so we're going to just move along the cost curve in this way. So we need to be able to calculate the gradient of our cost or error, and that's depicted with epsilon here, with respect to each of the weights and the intercept. Those are our goals. Applying the chain rule, we can break them up into two pieces. So the gradient of the cost with respect to the predicted y hat, and the gradient of y hat with respect to the weight. So let's calculate those. The gradient of y hat with respect to w naught, say, is pretty simple. So all of the terms are constant with respect to w naught, so except for the one on the left. So all of the others go to 0, and we're left with x naught. For the second gradient, we're going to just bring down the power, and then apply the chain rule internally to bring out the negative sign. So that's the gradient of the error with respect to y hat. So to get our final desired gradient, we just multiply those together to get this expression. And this goes for all of the weights. As for the intercept b, we can consider that a special weight where the x that it corresponds to always takes the value of 1. So we can just substitute 1 into x in that previous equation. So this is the form the gradient will take with respect to b. And that's how the code will look like in NumPy. We first calculate the delta between the true y and our predicted y hat, and then we just calculate the gradients correspondingly. And then what we want to do is update the parameters. We want to move the weights in the direction of the gradient, and we do that by subtracting the gradient from the weight. Now, but there's a possible problem here, because just like when you're practicing basketball, you may overcorrect. You're too far to the right, you adjust your angle to the left, but you wind up throwing your ball too far to the left. So you move right, and now you've overshot in the other direction. And maybe you're getting angrier and angrier with yourself, so you wind up even more wildly off as time goes on. And we can do this in gradient descent also, and it's called overshoot. Or you might have the opposite problem. You're too timid in making your corrections, so it takes you forever to get to the minimum. You converge really, really slowly. And if you have a cost curve that's uglier than this, with lots of local minima, if you're taking steps that are too small, you may get stuck inside that local minimum. So that's a bad situation. So what we're going to do is to try and be Goldilocks. We're going to aim for something in between those two. And we regulate this, how big of a step we take, using a hyperparameter called the learning rate. And the larger the learning rate, the bigger the step you take. Putting all that together, here's how training goes. Whatever our current weights and intercept are, we calculate our prediction. Then we calculate our error, we compute our gradients, and we update our parameters via gradient descent. That was a single round of training. So the entire training process involves first initializing our parameters and doing some number of training rounds. Whatever the weights and intercept are at the end, that's our final model that we're going to use to predict. Testing is going to be really simple. We get our estimate and figure out how far off we were on average. And on this particular housing data set, we were about $6,000 off per house. OK, so you may be wondering at this point, I came here to hear about deep learning and neural networks. Why are we doing something so basic as linear regression? And the reason for that is, surprise, we actually just made a neural network. Linear regression is one of the simplest possible neural networks. It's so simple that we don't even call it that because it preceded neural networks. But if you look at the definition of a neural network, linear regression fits the bill exactly. We have an input layer consisting of those three x to x sub I input neurons. And we have an output layer consisting of a single neuron. And we have weights on the edges between those neurons. That's exactly what a neural network is. So now we know that linear regression is simply a neural network in disguise. We can rewrite it in TensorFlow. And what we're going to do is to take those 7 ingredients that we went through in NumPy and just recast each of them in TensorFlow. So ingredient 1, inputs. So already this looks very different. Instead of supplying the data directly in NumPy arrays, we're going to have something called placeholders. And this X placeholder says, I'm going to be a matrix of floats, and I'll have 3 columns. The none here means that I'm going to push through a variable number of houses each time. If you want, you can specify a specific number here, but then you'll be stuck with it. You always have to put through like 60 houses at a time. So for flexibility, we'll just say none. Similarly, the Y placeholder corresponds to a single value. So it'll be a single column. Our parameters will be represented by TensorFlow variables. So we're mapping 3 neurons to 1. So the shape of our weights will be 3 rows by 1 column. And we can specify here how we want to initialize our weights, which will sample from a random normal distribution. And the intercept we're going to set to 0. Our operation will be matrix multiplication followed by addition. And our cost function just looks like this. Reduce mean just means mean. Now, the optimization step. We'll specify that we're using gradient descent with a certain learning rate, and that the quantity we want to minimize is the cost that we just defined in the previous slide. Now for the training process. So first of all, notice that we're going to do this within a TensorFlow session. In TensorFlow, nothing happens outside of a session. All you can do is define variables. It's only within a session that you can start writing to the CPU or GPU and performing computations. You can't even add 2 numbers in TensorFlow without going into a session. Okay, the next thing we do is to initialize the variables according to how we defined them earlier. And now we're going to go through the actual data. So xtrain and ytrain here are actual NumPy arrays. And we're going to use minute batch training, meaning that we will random.shuffle the data and feed the data through small batch by small batch. And we pass these batches into the optimizer, inserting them into the respective placeholders. So that's training. So here's all of that previous TensorFlow code in one place. And I want you to notice a couple of things. So first of all, remember all of that math that we did to calculate the gradients? So the NumPy code that came out of that is gone. Okay, it's disappeared. The other thing is that the code is divided into 2 parts, the part outside the session and the part inside the session. And I want you to think of that first part as like the blueprints for something, while the part within the session is like actually building that thing. And that thing that we're building is called the computation graph. And this is where we take all of our variables, all of our operations, all our placeholders, and sequence them together. So here we have the dot product and the addition of the intercept. But that's not all the computation that we need to do. We also need to compute the error. So let's add that on. Okay. So what do we do with the computation graph? So first, we do a process called forward propagation. We take our current weights and the x's and y's that got fed through and propagate them through the graph by performing the designated operations. So forward, we get a y hat, and then we compute the error. And that corresponds to these 2 lines from our NumPy code. Next, we need to calculate the gradient of the cost with respect to each of our variables. And this process is called backpropagation, or backprop for short. So we start at the end and work backwards. First off, we have the derivative of the error with respect to the error, and that's just going to be 1. And from this point on, what we're going to do is calculate the local gradient at each point and multiply it by the gradient computed up to that point. So let's work through a concrete example. The function here is just taking the square. The derivative of that is just 2 delta. Delta here was -2, so our local gradient was -4. And we multiply that by the gradient calculated so far, 1. And so the gradient of the error with respect to delta is going to be -4. And we're just going to do that over and over again, backpropagating through the graph. You're welcome to download the slides later and work through it yourself. And finally, we get that the gradient with respect to W0 is -8. And so we can just check, right? That's -2 times the delta, -2, times its corresponding x0, also -2. So that's -8. So that corresponds to what we did in NumPy. Okay, lastly, we have to update the variables. So let's just drop everything that isn't a variable. And then we just take the weight, W0, and we update that to the top number minus the learning rate times the bottom number, which was the gradient, and we get our new weight. And we can do that for all of the weights and the intercept. So that corresponds to these 2 lines in our NumPy code. And I just want to take a moment here to appreciate how much work TensorFlow saved us. So all those lines of code in the previous slide basically correspond to this 1 line of TensorFlow code. Once we define the computation graph, which is implicitly encoded in the optimizer variable, then all of the steps within the training were handled by TensorFlow, including the gradient computation, which wasn't very painful in the case of linear regression, but it can get tedious really fast once we start adding more layers and operations to our model. So thank you, TensorFlow. All right, our last step is going to be testing. So within the same session, we run a separate set of data, xtest, through the model to get our predictions, and we compute the error. OK. So that was linear regression. But what if we want to do something pretty different? What if we want to do classification? So an example classification problem is the MNIST data set. These are small images of handwritten digits, 0 through 9. And our features are the values of the pixels, and we're trying to predict which digit is which. Now, before we get to the 10-way classification case, let's talk about how we would tackle this if we were just doing binary classification. We have a bunch of samples that are positive and a bunch that are negative, and we want to be able to classify them. And we can do this using logistic regression. Our model will be this. So first take a weighted sum of the features and add a number that we'll call the bias. This should sound a lot like linear regression, except that we give the output a funny name, the logit. Then we'll convert the logit to a probability of belonging to the positive class via the logistic sigmoid function. So this is what this looks like in neural network graphical style. We compute the logit and then apply this nonlinear activation function, which I'll depict with this red semicircle. And this is what the logistic sigmoid function looks like. And the key thing to note is that it's between 0 and 1, so it gives us something that looks like a probability. So how exactly do we do classification with this? So we'll take 0.5 as our cutoff. If the probability is greater than 0.5, we'll declare a sample positive. Otherwise, it's negative. And the further away you are from the line in the positive direction, the more likely you are to be a positive sample. OK, now let's go back to the 10-dimensional problem. We'll have 10 neurons in our output layer corresponding to each digit. And therefore, we'll have 10 times the number of weights and 10 different bias terms. We'll also need a way to turn those 10 logits into probabilities. We can't just apply the logistic function to each of those logits, because that won't give you numbers that sum up to 1. Instead, we're going to use the softmax function, which is just the multinomial version of the logistic sigmoid function. So it takes all of these logits and transforms them into a probability distribution. OK, so that's the graphical representation of that. The box is just to show that so it's red, so it's the same function, but the box shows that it's operating on all of those neurons at once. And we can start coding. Oops. All right. So our X placeholder is going to have 784 columns. That's because our images are 28 by 28 pixels. And we're going to use one-hot vectors to encode our digits, with a 1 in the position corresponding to the correct digit. Now for the variables. So we're taking 784 input neurons to 10 output neurons. So our weight matrix will be 784 by 10. And we have 10 separate biases, one for each output neuron. Our operation is going to be matrix multiplication again. And you're probably thinking, wait, we're missing one operation. What happened to softmax? But remember from the computation graph that the model and the cost functions sort of meld into each other. So we're just going to push that into the cost function. So this is the cost function. We're going to use softmax cross entropy. And you can see that this particular function expects logits and does the softmax internally. If we computed the softmax in the operations part and then supply the probabilities to this function, we'll be implicitly doing the softmax twice, and that's wrong. OK. This cross entropy, incidentally, is a cost function that's very commonly used in classification. And what it basically says is, whatever the correct y is, I want the probability of being that y to be as close to 1 as possible. And it imposes a logarithmic cost for your distance as you go away from 1. OK, optimization. Our optimization code is exactly the same as in linear regression, and ditto with the training code. Testing is a little bit different, because when we compute how accurate our classification algorithm is, we don't want to use the vector of probabilities. We want to get back a one-hot vector with our predicted digit. So we'll define a new operation called predict that takes the R max of the logits. So we run our test data through this operation and get the predictions, and we can compute our accuracy, which in this case is 92.5%. This may sound pretty good, but it turns out that 92.5% for MNIST is pretty bad. The state of the art on this task is upwards of 99%. And one reason for this is that we're using a linear model, and linear models are pretty weak. So here's something that we can't classify using a linear model. When all you can do is draw a straight line, you can't approximate a function like exclusive OR. And you can't do something like concentric circles either. So what can we do? Well, I've heard that there's this magic thing called deep learning. So we're going to try to go deeper and see whether we get a good result. So what we're going to do is to add a hidden layer to our neural network. It's called hidden because we have no idea what its values are supposed to be. We know what our x's and y's are, but we have no idea about the values of those internal neurons. So we're going to need 2 sets of weights and biases. And we'll do 2 rounds of matrix multiplications. The rest of the code is just the same, so let's check on our results. OK. All right, wait a minute. So I was told that going deeper was going to help, but my accuracy actually went down. What gives? Is deep learning just hype? So the problem is that a linear transformation of a linear transformation is still a linear transformation. We need to find a way to add nonlinearity to the system. And we already know how to do that, right? So before we applied a nonlinear activation function to our output neurons. Now we just need to do the same thing for our hidden neurons. And there's a whole bunch of nonlinear activation functions that you can consider. Some of them work better than others. And the one on the right, which is called rectified linear units, or ReLU for short, is pretty popular. So we'll use that. Oops. OK. So we'll just amend our operations to apply ReLU to the logits of the hidden layer. And yay, our accuracy went up. So what exactly did the hidden layer bias? Well, it can classify things like exclusive OR. So here's what the classification boundary looks like. And I think this is with 4 hidden neurons. We can also classify concentric circles with 3 hidden neurons. So let's take a look at how classification boundaries change as we add more hidden neurons. So this is a data set that's a little bit like XOR, but it's 3 by 3. And this is what the classification boundaries look like with 2 neurons. And you can see that as we add neurons, our classification boundary gets more and more complex until we can perfectly classify everything. So what we did here was to transform our 2D space into a 5D space where the positive and negative samples could be linearly separated. So we saw that we could make our classification boundary more and more complex by adding neurons to the hidden layer. And it turns out that there's a theorem that says you can approximate basically any interesting function using a single hidden layer. You may need a lot of hidden neurons, and it may be almost impossible to actually train, but theoretically, it exists. OK, are we deep learning yet? No. So we only have one hidden layer. And you don't qualify as deep until you have at least 2 hidden layers. So I'm sure you can guess by now how to define the variables. And as for the operations, we just need to add another round of matrix multiplication and ReLU. OK, just a couple of slides ago, we said, using a single hidden layer, we can approximate just about any function. So why would we ever need to add more layers? And there are 3 reasons for this. So the first reason is that deeper networks are more powerful. So there exist functions that can be approximated in a deep network with, say, k layers, containing a number of neurons that's polynomial in the number of inputs. However, if we take even one of those layers away, we have k-1 layers, we would need an exponential number of neurons in our hidden layers to be able to approximate the exact same function. The second point is really a bit more about narrow layers, but deep and narrow sort of go together. So narrow networks are less prone to overfitting. And when I say overfitting, I mean something like this green boundary over here, which is so determined to get each and every point in the training data right that it sacrifices generalizability. Now, the thing is, if you're funneling your data through a narrow layer, you're going to have to make some tough choices about what information to pass through. You can't just say, I'm going to allocate these 5 neurons to take care of that one outlier. Instead, you have to figure out how to communicate the best features of the most useful features of your data as best you can when passing the information on to the next layer. Incidentally, this is the principle behind auto-encoded networks, which are a neural network where you're just trying to predict your input data. So this sounds really trivial to do, right? Except that you're pushing it through this really narrow layer, which forces you to come up with a compressed representation of it. And then you can use that compressed representation in place of your sparser representation when doing some other task. OK, on to the third reason. And this is probably the most important reason for going deep. So deep networks learn hierarchical feature representations. We can see this most clearly when we look at the kinds of neural networks that are used in image classification. We input the pixels and get out a determination of the object seen in the image. And if you examine the kinds of features that each layer is detecting, you'll see that they build on each other. So at the first hidden layer, it's detecting things like edges. And the next layer is putting together edges to find things like corners. And then at the next layer, maybe have 2 round things over a curve, and it says, aha, I see a face. And we go up and up until we can say, this is a person. And one trend that we see as a result of this property of deep learning is a movement towards end-to-end learning, where you feed in the rawest form of your data, like pixels and characters, into your system, instead of first computing hand-engineered features. The deep learning system learns all of the levels of the features for you. OK, so let's go deeper. All right, that didn't really work out so well. And when this happens to you, there are a couple of things you should consider. So first of all, is this a problem that requires a deep network? Maybe solving the problem requires combining the features in very simple ways, in which case a deep network doesn't really do anything for you. The other question, which I suspect is more often the problem for most of us, is do I have enough data to train a deep network? To go deep, we need a lot of data, and MNIST is not a large data set. If you do have a large enough data set, however, you can expect your test accuracy to gradually increase with the number of layers. But we don't have that. Instead, what we see is that we have overfitting. Our training accuracy increased, but our test accuracy went down. And I said before that overfitting was something shallow networks with wide layers were more prone to. But you can also get overfitting with increasing layers because that increases our model complexity. So what do? We do regularization. So the idea behind regularization is this. Up till now, our data has always been in the driver's seat. Whatever the data says goes. If I have an outlier over here, and there's no other data points to argue against it, I'm going to contort my boundary to accommodate that layer, the outlier. Now, what we're going to do is to put the brakes on the training data using regularization. And we're going to do that by enforcing constraints on the parameters that we learn. So you're probably familiar with L1 and L2 regularization, because you also see them used in linear logistic regression, SVMs, etc. And what L2 regularization says is simply, I want my weights to be small. And it does that by imposing a cost or loss on the weights. That's the sum of the squares of the weights. So the larger the weights, the bigger the cost. And we'll add that regularization loss to our existing data loss, which we already encoded into the cost function. And we have another hyperparameter here that determines how tightly we're leashing the data. And here are the results. That's pretty good. Now, let's talk about a different regularization method, which is called dropout. This isn't really applicable to linear methods, but it is something that we can do once we have hidden layers. And what we're going to do is this. At each training step, we're going to randomly knock out half of our hidden neurons. Okay. And at first glance, this may seem like a really crazy idea. Why would we want to forfeit half of the modeling power of that layer? Why would we want to lose half of the information in our weights? Well, we do it because it works. And here are some reasons people cite for why it works. So firstly, every time we drop some neurons out, it's like we're building a completely new prediction model. And when in the end we take all of the neurons together, it's like we're averaging together all of those models. So if you're familiar with ensemble learning, it's just like that, except that you're doing it internally. The second reason is that it forces useful features to repeat themselves. And that makes our network more robust. The third reason is that, well, you can't have a good conspiracy if your co-conspirator might drop out at any time. So hidden neurons must be individually useful. And again, we can't have 3 neurons over here conspiring to accommodate an outlier, because 1 or 2 of them may be missing at any time. OK, so during training, we drop out half the neurons. But at test time, we want to keep all of those hidden neurons. But that creates a problem. Right? Our logits at each point are going to be twice as big as they were in training. And to solve that problem, what we're going to do is that at training time, for all of the neurons that stayed alive, we'll multiply all the logits by 2. OK, so now let's look at how we do that in TensorFlow. So the first thing we do is to add a new placeholder. And what the placeholder does is to define the probability of keeping a neuron. And we usually set that to 0.5. And then we're going to add a dropout operation between the hidden layer and the output layer, supplying it the keep probability. And during training, we pass it a keep probability of 0.5, which drops out half of the neurons. And during test time, we supply it a keep probability of 1.0. And TensorFlow will handle all of the dropping out of the neurons and the scaling of the logits. Another thing to note is that training is generally a lot slower with dropout because you're considering all of these different models. So you want to bump up your number of training rounds. OK, so this was the accuracy that I got. A little bit better. All right, so where do we go from here? So we saw that there were a number of ingredients we had to define and consider in every single model that we created. These ingredients also constitute a good roadmap for exploring deep learning further. So we're going to ignore placeholders and cost function because those are pretty much problem-driven. We also saw that training and testing don't differ much by problem. So let's look at the others. In terms of variables, we can consider varying the number of hidden layers and the number of hidden neurons per layer. We can also explore different methods of initializing the variables. So here I use random normal, and I use the constant initializer. But you can try things like random uniform, truncated normal, etc. You can also consider different nonlinear activation functions. So ReLU is the current recommended starting point, but you can play around with all these others. You can also consider an entirely different architecture than feed-forward neural networks. If you're doing anything with images, take a look at convolutional neural networks. And if you're doing anything with text, sequences, or time series, then look at recurrent neural networks. OK. We used gradient descent exclusively in this talk, but it's actually one of the slowest converging optimization problems. And this GIF is the red straggler. And the current recommended one to try first is the Atom optimizer, so just give that a shot. It's all in TensorFlow. Lastly, there are a bunch of regularization/optimization techniques that can help with training and reducing overfitting. So in this talk, we looked at L2 regularization and dropout, but also check out L1 or batch norm and layer norm. Also, in this talk, I used the TensorFlow library exclusively. But there are lots and lots and lots of other deep learning toolkits out there. And these are just some of that I've heard good things about. So you can try those. All of the steps that we defined before will apply also in other toolkits. I also want to give a plug for Keras. So this is a higher-level library that sits atop of TensorFlow. And there's also a Theano backend. And Keras is sort of to TensorFlow as scikit-learn is to NumPy. And it simplifies things considerably. So this is how the TensorFlow code that we've been using, that we've been working with so far, translates to Keras. And hopefully, with the background provided in this talk, you can go through this and understand what's happening in every line intuitively. OK, final thoughts. First is that if you're familiar with traditional ML, I hope I've convinced you that you can do deep learning. But in order to do deep learning, you will need data, lots of it. So what I recommend is trying traditional ML first and just seeing whether it works well enough for you. And if it doesn't, then go on to try deep learning. And just go forth and experiment. Thank you. OK, I can do a couple questions.
Thank you, everybody. We've probably got time for one question. If anyone has a question, there are microphones in the aisles. Oh. Just over there. Oh, hang on. We have one here.
Oh, OK.
So in a statistical analysis, you usually need a reason to choose one tool or one particular analysis technique over another. Do you need that here if you were to pick a different activation function or any of the options you have here? Should you just play with them until you get good accuracy, or do you need to kind of have a justification for that? OK.
Did you hear that? I'm sorry. Can you just say that again really slowly?
In statistics, you typically need a reason to use a particular approach. If you're going to take the log of your data, you have to have some theoretical reason for that. Yeah. Do you need a similar thing here, or can you just use a different activation function because it gets better accuracy and that's good enough? OK. So the question was about, are there basically considered reasons for using one activation function over another? And there are some. So
Let me see. Can I go back? OK. All right. So what? OK. Well, OK. I'm not going to look for the slide. What you can do is, so there are reasons for certain activation functions being better than the others. So for example, hyperbolic tangent is like strictly better than sigmoid function. And I don't actually exactly remember the reason for that. But one reason that people use ReLU over like the sigmoid and the hyperbolic tangent functions is that it has like more room to grow. It doesn't get capped at between -1 and 1 or between 0 and 1. And as a result of that, it's better for doing deep learning because you can like propagate the gradients better along the various layers. Whereas if you're doing the same thing with the capped activation functions, then you're going to have a problem where everything gets squished too much, and you don't actually get a lot of movement on your gradients. OK? Is that it?
Thank you again, Michelle.